Morning, all.
Today I wore my yellow shirt.
All right. Yeah, I've decided to go all gray today. Match the weather. Also, just what happened to be on top of the pile of clean clothes. So my usual approach to picking out my outfit. Okay. Let's see. Oh, I need the chat window open. Hang on. Oh, I have the chat window open. Yeah, exactly. It is too much work. Yeah. Whatever's on top. Um, so
You see, the secret is the yellow shirt was on top.
yeah, there you go. Um, or you can take the Steve Jobs approach and just get all of the same clothing. It's also apparently the Einstein approach, just all of the same thing, and then it's just you never think about it.
One could always not turn their camera on,
Yeah,
but it
that's
doesn't
true
matter
too.
what you wear.
Yeah, it did occur to me that once the pandemic is over, maybe I'll have to stop wearing running shirts to work. Um, So certainly by fall, yeah, those of you who are, oh yeah, none of in this class, my other class, most of the people are seniors or juniors. And so this is like the end of their college career is just somebody saying bye over Zoom. Um, but for all of you, right, come fall, you'll be back on campus. I know that that's at least the plan, that things will be normal by fall. We may be wearing masks on campus, but at least we'll be back. Uh, okay, let's start. We've got so this is the last chapter we're going to do, and it's on inductance, and it's very closely related to Faraday's law. It's essentially a definition that comes out of Faraday's law as a consequence of Faraday's law. Um, so, well, first I'll ask you a couple of questions, and then we'll get to the definition of inductance, which is not too complicated. It's really just some of the signs are subtle in this chapter, and a couple of the details are complicated, but it's not too bad. In some ways, the previous chapter is a little harder. So let's suppose that I have a simple circuit like this. I'm going to just have a resistor and a battery with some voltage and a switch. When I close the switch, so when switch is closed, then current goes from 0 to, right, when the switch is closed, your current in this, if this is an ohmic, if this resistor follows Ohm's law, this will go from 0 to V over R. Right, so the current in the circuit, that, right, it'll be V over R once the switch is closed. But now there's a funny thing about this. We've been saying, all right, you close this switch and then time equals 0, the current instantly goes from 0 up to its maximum of V over R. So there's an instantaneous change in current. But if you think about it, there's something funny that happens here. Our goal here is to understand, how does the current increase? It really can't go from 0 to V over R instantaneously. And why not? Well, think about what would happen. When switch is closed, current starts to flow. Okay, good. So what happens then? All right, so I close the switch, and let's just suppose that it doesn't go to V over R instantly. So as the current goes from 0 and starts increasing toward V over R, what happens? Well, there's now, when this switch is closed, now there's some current I going through here, and it's going from 0 up toward V over R. But as it's going, right, it's now running if you have current like this in a loop, you know, following the right-hand rule, that there's a B field going into the page through this rectangle because there's now current flowing in the circuit. Okay, so there's current flowing in the circuit, there's a B field going in, so you know what happens. If let's forget about this problem. Suppose I have, forget all about that. Suppose we go back to the previous chapter and I just say you have a rectangular loop of wire and I have a B field that starts at 0, and then at time equals 0, I start dialing up the strength of the B field and it's into the page. All right, so quick use as a review, use Lenz's law to figure out the direction of the induced EMF in this. If at time equals 0, I had no B field, and then I start cranking up the B field and it points into the page. What's the direction of the induced EMF around that loop? So just take a minute and, you know, do the Lenz's law of it saying it doesn't want change in flux. So figure out if it's counterclockwise or clockwise induced EMF. Let me see if I have a poll for this. Hold on. I should do this as a poll because I want to see how many people get this. Shoot, I don't have a clockwise or counterclockwise. Here, just here, I'm going to launch this poll. So I want to see how many people get this right. So pick the direction. Let's say, so there's an induced EMF either this way or this way. And so the induced E electric field here will be either to the left or to the right. So if it's counterclockwise, the induced electric field here will be to the left. If it's clockwise, the induced E field up here will be to the right. So vote which you think it'll be, left or right up here. So left if you think the EMF is counterclockwise, right if you think it's clockwise. All right, I have a lot of abstentions. Don't vote up or in, none of the other votes, none of the other directions matter. Left if it's counterclockwise, right if it's clockwise.
Wait, the X's mean it goes into the page?
Yep, the B field is going into the page. So forget all about inductance. B field is going into the page and it's getting stronger. So, right, so the loop says, no, I don't want more ingoing magnetic flux. And if you're using Lenz's law, and so it tries to run a flux going out. It runs a current that's consistent with a flux coming out of the page. Okay, so there's still a lot of confusion on the directions. I'm just going to end the poll. Yeah, so a lot of people got this wrong. So the induced EMF will be this way. And so there will be an induced EMF around that way. So the answer was left on the top. And the reason is because if you have a B field going into the page and increasing strength, and the loop says in this anthropomorphic Lenz's law way, it says, no, I don't want increasing downward flux through this. So it will run a current that would make upward going flux through itself. And that would be a current that goes this way, because a current that goes this way around a loop, if you use the right-hand rule, a flux will come out of the page through its center. So this will generate, this case will generate an EMF that goes that way. So here, when you close this switch, you increase the current going this way, which generates a back EMF, an EMF that goes this way and sort of opposes that change. So the current, and we'll do this quantitatively in a few minutes, but the current can't instantly jump from 0 to V over R, because that would be an infinitely steep change. And that would be an infinitely steep, right? You know, E induced EMF is minus d phi B dt. So just qualitatively for now, if the current went instantly from 0 to V over R, the B field would go instantly from 0 to something, which means this is now infinitely large. The time rate of change of the flux through this would be infinitely large, which means there'd be an infinitely high induced EMF. So it's not going to go instantly from 0 to V over R. It's going to take some time to do that. Okay. So question so far? All right. So Jeff, if it was decreasing, would it be going right counterclockwise? Yeah, Jeff, we're going to answer that in just a second. The short answer is yes, but we'll do that properly in a second.
Just by looking at it, how do we know if it's decreasing or increasing? You
Oh.
give it to us, right?
Well, in this case, it's not that I gave it to you. It's that we started with a circuit where the switch was open, and so the current is nothing. And now if I close the switch, obviously the current was nothing, but now the current is increasing this way. And so if the current is increasing, a loop with a current going this way makes a B field into the page in here.
I see it. Thank you.
Right. Okay. So now, but let's do, I think your question and Jeff's question are sort of related, right? So now let's do the other case. What about when we open the switch? So let I reach V over R, then open the switch. Okay, so now we have a something like this. It's carrying current I of V over R. Sorry, here's our battery V and our resistance R. So this thing is carrying current V over R. It's just nice and steady. You have a B field going into the page, not externally, a B field going into the page because we've got a loop of wire with current going that way. So now open the switch. What happens when you open the switch? Well, when you open the switch, the current wants to run from V over R down to 0 now. So the B field is inward into the page through this loop, but it's getting weaker as a function of time. So in this case, we induced an EMF that was this way in this loop. In this case, now as the B field, the inward going flux decreases, the loop says, no, I don't want, in Lenz's law way, I don't want the decreasing flux. And so now it will create an induced EMF to increase the inward going flux, which would correspond to an induced EMF that's this way. Right? So this will oppose, in each case, the induced EMF will oppose the change in current. Right? And this actually, you can see this in ordinary experiences. If you have anything that's closed, if you open a switch, or if you look into a light switch, when you turn it off, you'll often see a spark across here. Not when you plug something in, but when you unplug it. Because at the moment you unplug it, right, at the moment you break the connection there, if you look close up at that spot, so here's the switch, and now you've just barely opened the switch, and the current has been whatever, it's been, there's some high current running in this. As soon as you open this switch, now the current is going to fall, but you will induce this EMF around this loop, and that will create a voltage difference between these two sides of the switch. And when they're very close together, it's right. So the E field is volts, joules per coulomb, or equivalently volts per meter. So if you have a voltage difference and two things that are extremely close to each other, you'll have a very strong electric field here, because you've got a big voltage difference across them. And so you have a very strong electric field here, and that'll, if it's, when they're close, that'll ionize the air between them in that gap and make a spark. And this actually in industrial applications and engineering applications, this is a huge deal. This idea of things sparking. You can't write in aircraft, you can't have things sparking every time currents are switched up and down and switches are opened and closed. And so things don't just things are not just suddenly opened and closed. Currents have to be ramped down. If you really wanted to open this switch and it was something where you cannot have a spark, you have to dial the current gradually down to zero or a very low level, and only then can you open the switch. And in fact, an old friend of mine worked on actually the transformers that change the frequency of voltages off of windmills, turbines, thank you. And that's a huge problem there, because you're carrying all these high voltages, and you cannot have people in there just turning things on and off, because if you have a high current, right, the whole thing will just explode if you make a huge spark across it. Right, if this is carrying tens of thousands of amps, you can't just shut it off. And so most things have switches or mechanical motorized switches. So you may pull the switch, but the switch won't open then. The switch will automatically wind the voltage down to zero, or wind the current down to zero, and only then release the current. Only then open the switch. Okay, so Alistair, Jeff, does that sort of answer your question about other directions and opposite way? All right, just pipe. Okay. So let's look a little more qualitatively or quantitatively at this idea of inductance. So you would say that this rectangle has some inductance. And inductance basically means an opposition to having the current change in an object. You know what a resistor is. A resistor is an object that has some opposition to current flowing through it. An inductor, as we're going to see, is an object that has an opposition to the amount of current through it changing. So resistors oppose current, inductors oppose changes in current. So to do this more quantitatively, let's look at something not just a rectangle. Let's look at a system that we've worked with before. So to start this, let's say I have a coil, so a helical coil or a solenoid. Right, so you imagine I've wrapped thousands of turns of wire around this glass, right? So this way, thousands of turns. So I would have a solenoid. I'm just drawing kind of expanded, crazy view of it. And let's suppose I have a current in each loop that's going this way. This is the front. And so if you're looking down on it, you're looking down on one loop. You have a current I going through each loop. Okay, so if you have that, then what happens is that means as you try to change the current in this, right? So when current I is flowing, there is some magnetic flux phi B that's going up through this coil, because each loop has a current in it, and so has a B field that goes up, and so there's each one of these loops makes a magnetic flux that goes all the way up through all of these, because each loop makes a B field. And so it makes a flux through all of these. So there's some flux going through the whole thing. And if I try to change the current through this, let's say I wire this thing up to, let's say, I don't know, a resistor and a battery. If I try to change the current that goes through this, we know that this thing will produce a backwards EMF. When I try to increase the current through it, it will. So let's say this is adjustable. When I dial this voltage up and try to drive more current through it, this will make an EMF that points the other way. And when I try to reduce the current by lowering this voltage, it'll make an EMF that goes, again, the opposite direction. So we'll always oppose changes in the amount of current through it. And one thing you should notice is here at this point, I stopped worrying about the fact that as I change the current in here, this loop itself creates some magnetic field and some flux through the rectangle. The basic idea is that we're going to say, look, if I have a coil of 1,000 turns, this is going to be where most of the opposition to changing the current is going to be. Most of the induced EMF is here. Yes, there's a little bit in this rectangle of the circuit itself, but we'll just say this is small. So we're gonna, but technically, yeah, this has inductance and this has inductance, and you would have to find the total of them. But for our purposes, let's just worry about what the effect of this coil is on changing the current in the circuit. Okay, so what we know is, so we're going to do this quantitatively, or at least introduce this definition quantitatively, right? You know that Faraday's law tells us that the induced EMF is minus d phi b dt. So does that mean that the E field is switching back and forth all the time in an AC wire? Yeah, so if you're running AC and you're trying to switch the current to go back and forth, yeah, the inductance in this will oppose, if you have an inductor like this wired into it, yeah, it will continuously oppose the change in voltage. The voltage will still change, but it won't change as quickly as it would have. It'll have to ramp its way up and then ramp its way back down, right? Because this will basically slow it down. Okay, so we have Faraday's law, and so let's try to quantitatively introduce a definition of this. So our definition of inductance right? And again, with a lot of these definitions, if you try to imagine yourself having to cook up the definition, you'll usually come upon either the right definition, or if you don't get the right definition, it'll help you understand why the right definition makes sense. So the definition of inductance, L, there are actually a few definitions I'm giving. This is pretty much the same one your book uses. Okay. So if you think about what would you want for a definition of inductance, how much does this thing oppose a change in current through it, right? So you can imagine if I have a coil of 100 turns, when I try to change the current through it, it generates a backward EMF of some amount. And now if I have a coil of like 50,000 turns, when I try to change the current by, let's say, 1 amp per second, that is going to generate a whole lot more flux through the coils because there are more turns in it. And each loop in the coil has a magnetic field and generates a flux. And so the more turns I have in this coil, and maybe the size and the shape of it will change how much backwards EMF the coil produces in the circuit. How strongly does it oppose having the current change through it? And that really brings us to the definition of inductance. So the units of inductance are henries, named after Joseph Henry from Albany. So it is the volts of EMF, volts of opposing EMF for every amp per second of changing current. All right, so it really is, it's the thing you would like to sort of know. You say, okay, if I change the current in this thing by 1 amp per second, so you can move this over, you can say EMF, backwards EMF is L times di dt. How many volts of backwards EMF, opposing EMF, will be generated for every amp per second? If I crank up the current at the rate of 1 amp per second, how many volts of backwards EMF will be generated? That's L. The number of volts back EMF for every amp per second that you dial up the current. Now, of course, if you tried dialing up the current at 2 amps per second, so you go from 0 to 2 amps to 4 amps, then you're going to get twice as much backwards EMF. But it's the ratio of those two things. Just like you did with just, V equals IR. It's how many volts do you need to drive 1 amp of current through the object? That's the thing's resistance. And then here, it's how many volts of back EMF do you produce for every 1 amp per second that you try to increase the current. Okay, and again, the units of this are henries. Okay, so questions so far? And then we're going to actually calculate L for a solenoid. Okay. Sorry, give me a second here. Just need a placeholder in chat so I know when there's a new question. Okay, so let's, you sure no questions so far? You briefly go over E surrounding the solenoid again. What do you mean E surrounding the solenoid, Jeff?
Just how like one side goes up and one side goes down.
Oh,
I missed that.
yeah. Be careful in the way I drew this. I don't mean E is not going up one side or down the other. These are two different cases. If you look straight down at this solenoid like this, so now you're looking at it and you're looking into the solenoid. If there is a current going this way in it, then there's magnetic flux coming up through it. And if you try to increase the current, then there will be increasing magnetic flux up through this thing. And then through Lenz's law, it will say, no, I want to generate an EMF to make downward flux. And so it will, so if I is increasing, if I is going this way and increasing, then there will be an EMF that's induced that way. So that's one case.
Okay, thank you.
And then the second case is, so still looking straight down on that solenoid. Let's say the current is still going this way, but let's say now it's decreasing in strength. So now, because the current is going this way, you still have an upward going flux, but because I is decreasing, there's less and less upward going flux. And so the thing says, no, by Lenz's law, I don't want a loss of upward going magnetic flux. And so it will run an EMF that opposes that and makes more upward going flux, which is this way. So be very careful. This is because remember, Faraday's law does not care about the amount of magnetic flux. It cares about the rate of change of flux. So you can induce an EMF either this way or that way when current is going this way. So notice I did not switch the directions of the current in these two examples. I just switched whether the current was increasing or decreasing. And so if we do the other pairs, why don't you quick write this down? Yeah, I'm glad you asked this, Jeff, because I needed a little more fleshing out. So let's suppose that the current is going this way and increasing. So for this example, figure out on your own, and then you can guess the fourth one we're going to do. Let's suppose, so again, you're looking down. This is not one loop. This is thousands of loops. Let's suppose the current is going this way and decreasing. Okay? So find the induced EMF, the direction of the induced EMF in these two cases. By thinking through, what direction is the magnetic flux, and whether is the flux increasing or decreasing, then use Lenz's law to find the induced EMF. All right, so just take a minute and do those out. All right. So let me give you another minute. Take a minute to really do this properly. Okay, so here the current's going this way, so there's magnetic flux inward, and it's increasing. Downward flux is increasing, so it wants to run its own current to oppose that, which means the induced EMF would be this way. In this case, the current is going this way but decreasing, so there is less and less. Sorry, hold on. Right, so there's less and less inward going magnetic flux into the page through it. And so the loop says, no, I want to run an EMF to make more downward going flux, which corresponds to an EMF that goes that way, right? So notice in all four cases, whether the current is going this way or this way, what matters is that the induced EMF is not tied to the direction of the current, but tied to the increasing or decreasing. When the current this way is increasing, EMF goes that way. So it's always opposing the change in the current, right? All right, so think about questions on this for a minute, and then we'll do a quantitative example of inductance. All right, so let's find the actual inductance in number of henries for a solenoid. And incidentally, in electric circuits, no matter what the shape of the actual inductor, they're always just drawn as a solenoid, like a coil of wire. Okay, so let's find the inductance of a solenoid, meaning we want to find out how much back EMF is generated for a given rate of change of current. Right? And this will actually not be too hard to do. Find L for a solenoid. All right, so what we really mean, since L is E over di dt, what we really mean is we want to know how much EMF is there for every amp per second of change in the rate of change in the current. So if I have a solenoid like this, what we know is that phi B, so recall B field for a solenoid, is mu naught I times little n, where little n is the winding number. This is turns per meter. Right, so if I have a coil, I can look at it on its side and count how many turns there are in 1 meter long segment. That's little n. Basically, it's a measure of how densely the coil is made. And I is obviously the current in it, and mu naught is the permeability of free space. So we've done this before, right? This is just the B field inside the solenoid. And so if I have a current going this way, there will be a B field going up through it. Okay, so phi B, let's first look at just the magnetic flux through one loop. Well, that's going to be equal to mu naught I little n times A, where A is the area of the loop. Right, so you have a solenoid. So right, you've got a slinky. You look at the end. It's pi r squared for the loop. Okay, so this is the flux through one loop, but that is not the flux we want. We need the flux through all of the loops. So phi B through solenoid is going to be mu naught little I little n A times capital N, where this is number of turns. So the total count of how many loops there are, not loops per meter, total count of turns. Okay, so good. So at this point, so we know at the end we're going to need this. So we can find the EMF. So the EMF of the whole thing is going to be equal to the time, if I'm changing the current. sorry, if I'm changing the current at the rate di dt, so E is going to be d phi, the magnitude of the induced EMF is the rate of change of phi b with respect to t. So we need to take the time derivative of this thing. So if you look at it, nothing, obviously mu naught, little n, a, and capital N don't change, but it's I that changes as a function of time. So the time rate of change of flux through this is just going to be mu naught, little n, a, capital N, di dt, right? Okay, so good. This gives us what we want. So now we know the relationship between the induced EMF and the rate of change of the current through the solenoid. So L is going to be E over di dt, or not di, right? So E over di dt, which is going to be mu naught A, little n, capital N. Okay. And then, so that's fine. So that's basically the answer. We're going to change it and write it in a different form, but that's basically the answer. So any questions on this so far? Okay. I should have, I'm going to make one little notation change. I should not, for L in this case, it's common to use script L, and I really should have for reasons you'll see in a second. So switch this to be script L, not capital L. I mean, it doesn't change what it is, but we'll try to use script L for inductance, and you'll see why in a second.
Professor,
Yeah.
would you mind just explaining number of turns to di over dt again? Like the phi through solenoid?
Oh, like why we got this?
Yeah.
Yeah. So if you know if I just take a single loop of wire and I say it's running a current, and you know the current, and you can find the B field, and you know the B field, then the flux through this loop is just B times the area of this, right? So it'd just be B times A. Is that okay, Jade?
Yep. Okay.
So okay, but now I say, well, fine, I have a B field, but I don't have one loop. I put a stack a second one on top of it. What's the flux through the whole thing? Well, now it's twice what it was, because you've got flux magnetic field going through two loops instead of one. And if I say, all right, well, now make a stack of 10,000 loops, well, it's be 10,000 times the flux through one of them. So that's how we went from here to here. Or the only difference is I just said, you need not the flux through one loop. I want the magnetic flux through the whole solenoid. So we got to multiply this by the number of turns.
Okay. Yep. That makes sense.
Is that was your question, or?
Yes.
Okay, good. Okay, so what else here in any of this? Right, mathematically, it's not super complicated, but it's a little subtle. Okay, so now you see the reason that I wanted to switch this to be script L is, suppose that it's a little weird to have turns per meter and total number of turns. So let's just suppose that our solenoid, it has little n turns per meter and its length is L, right? So then I could write this, and I didn't want to have L for two different things, obviously. So now I can rewrite the inductance of this thing as mu naught A, little n, and then capital N over L. Oh, sorry, I'm sorry. Stupid. Capital N is little n times L. So all I did was substitute in a very messy way. Capital N is total number of turns, is number of turns per meter times length, times meters of the solenoid. So I can write this as mu naught A, little n squared L. So that is the inductance of this coil. And it's common to write, you'll see in the book, so inductance per length. So when you read this in the text, you're going to see the inductance per meter for a solenoid is mu naught A little n squared. So the winding density. And so notice that this is, so questions so far? Sorry about that little confusion. Capital N is little n times L. Okay, so notice that this depends only on geometry. Meaning size, shape, whatever, right? So just physical properties of the object. So in the same way that you can have a capacitor, capacitors depend on just the physical properties of the object, not how they're being used. So that's why you can pick up a capacitor in a lab and it'll say how much capacitance it has. It doesn't need to know what kind of circuit it's being used in. An object has an amount of capacitance. In the same way, an object has an amount of inductance. So you could grab a slinky, measure, do pi r squared on it, count the number of turns per meter, how densely it's wound. That's its inductance in henries. Okay. Okay. So think about questions so far on any of this before we go on. We're going to kind of switch gears a little bit. So this is a good point to ask questions on any of this.
I don't understand the little n. Like, I understand it's like a density unit, but how do I visualize it in my head? Because I just don't understand where to put it.
Yeah, in fact, I wish I had, I lost, years ago, we got both our kids Slinkies for Christmas one year. And I borrowed one of them to use for lecture and I lost it. And I think I borrowed the second one and I think I've lost that too. So if I had a Slinky, this would be easier, but just imagine this is one. And so, right, it's a coil like this. If you wanted to know little n for this, you don't need a Slinky that's a meter long. You'd grab a little section here that's about a centimeter wide and you'd count. And I don't know, you'd probably find about 10 turns in that 1 centimeter section. And so you would say, oh, this Slinky has a little n of 1,000 because it's 10 turns in a centimeter. So it's 1,000 turns in a meter. Right? And that's it. Right? So it's not really, it's not a complicated idea.
And big N is just how many there are in total?
That's right. Yep.
Okay.
You just start at one end of the Slinky, count to the other, and that's capital N. Yep. And so it's a little bit of, it's kind of silly to, this has changed because it's a little silly to have little n and capital N, just write it in terms of one thing. You could switch it around and write it in terms of capital N too, but it makes more sense for solenoids to do it this way because then it's just inductance per meter. Right? Makes it easy if you're actually making a solenoid, you just, with a certain density, you just adjust the length to adjust its inductance. Okay. Yeah, Dan, it's not good. The real problem was the one that I lost, it wasn't clear whose I'd lost. And so which one of the two of them had one still was unclear because it was unclear whose Slinky I had lost. But now I've lost them both, I believe, and so it's fair. Okay, so one place you actually see, where did the L go in the one you circled? Yeah, so it's here, it's L per length. So you can really think about it as L divided by L is mu naught A little n squared. So inductance per length, or L over L.
Could you write that as scripty special swirly L equals, no, wait, never mind. I'm dumb.
Yeah. Okay, so good. So we just have that. One place, I mean, inductors appear all over the place. One place you encounter them is in anything that's a surge suppressor, either an external surge suppressor, or if you don't have an external one, your computer, your phone, they all have little inductors somewhere built into the power supply. And so, right, the idea is if you have let's not worry about AC versus DC. If you have something that's supposed to be feeding 110 volts into into the circuitry of your, your phone, your laptop, whatever, the problem is that electrical line voltage doesn't stay at it's AC, but it doesn't stay even perfectly AC. it has spikes and dropouts. And so you put a coil in here. And so what happens is if the voltage suddenly spikes up to 300 volts just for a little time, maybe a millisecond or less, if the voltage spikes way up, then all of a sudden this is trying to rapidly change the amount of current through here. If it could, you might fry whatever electronics are inside here. But what will happen is as soon as the voltage shoots way up, that'll try to rapidly change the current through this, and this will run an EMF that opposes that. And so essentially what it will do, and we'll do this quantitatively in a few minutes, is instead of having a line voltage that goes from 110 up to several hundred and then back down to 110, the inductor will essentially slow that. It'll rise exponentially for a while, except it'll flatten it out. And so you'll take the total amount of energy that this thing would have dumped into the circuit, and you'll spread it out over a much longer time. And in fact, if you read the back of a surge suppressor, it'll say that it can handle a certain number of joules of excess energy for a certain amount of time. Obviously, if the voltage goes up to 300 and just stays there, the voltage across here is going to go to 300 too. But if it's for a short amount of time and it's not too big, the surge suppressor will flatten it out and keep it within some narrow range around 110. Okay, so let's look. So questions so far? Okay, so let's look at a circuit and do this. So we're going to now use an inductor in a circuit and see how the voltage changes over time and how the current in the circuit changes over time. So this is what's known as a simple RL circuit. So this should give you a flashback, good or bad. Recall that we already talked about RC circuits. So you had to have a voltage and some resistor and some capacitor. And we tried to figure out what is the charge on this thing. What is Q here as a function of time? What's the current in the circuit as a function of time? So remember the current started at V over R and then gradually dropped to 0 over tau, where tau is RC. So you can flash back to that. So this was our current as a function of time. And then from there, once you know current is a function of time, you can find voltage across this as a function of time because it's the current times the resistance. And you can find the charge on this thing as a function of time, is the integral of this. Okay, so we're going to do the same thing, except now we're going to look at an RL circuit. So we're going to have a voltage and a switch that's open and an inductor of some inductance L and a resistor of some resistance R, and then back around. So the question is, when we close the switch, so this is our goal. When switch is closed, what is I of t? We know it doesn't just immediately jump to V over R, but eventually it will get to V over R, but how does it get there? Is it linear or what does it do? So we're going to do the same thing we did before. We'll do a loop equation. All right, so we'll do a loop equation. We'll start here and go around. So if I go around, I'll have plus V. I take a step up in voltage V here. And now here, be careful. The step down across this, the voltage drop across an inductor, is going to be L times di dt. Because remember, we have E, the EMF across an inductor is going to be, right? Our definition of inductance is E over di dt, right? And so the voltage drop, the EMF voltage drop from one side to the other is L times di dt. And so I'm switching back to just a regular L for this. I don't mean length, I mean the inductance of this coil. So that's the drop from there to there. What does that loop say? Oh, loop, this is loop equation. Right, so we're doing, Gavin. You know, same thing you did back in when we did two loop circuits with resistors and batteries. So we did plus V minus L di dt minus IR.
Just to clarify, you picked clockwise for your direction, right?
Yep.
Okay.
Yeah, I started here and went around that way.
So if it's
Yeah.
in the same direction as the coil, right? It's always a voltage decrease. Or I
Yeah.
mean a loop decrease or a
Yeah, well, if we went the other way, it would be a plus. And in fact, that's a good question. Right, you can kind of think, I'm glad you asked, I was meant to say this, right? You can kind of think of the inductor as a battery. So don't really exactly write this down, but there's some backwards EMF and a resistor here. And so this thing behaves like a battery that's always pointing against the direction that the current is changing, not against the direction of the current, against the change in the direction of current. So in this case, the current is ramping up. And so this thing acts like a battery that points the other way. And the question is, well, how big is this battery? If it's exactly V, then we already know the answer. If this were the same as that, then the current in the loop is zero. If it's tiny, it only has a small impact on the current we would have. And what we know is that the amount of this back EMF is going to be the inductance times the I dt. So you can see we're going to wind up with an exponential, and you should sort of start to see that appearing because you have something whose opposition to the current flowing is equal to the rate at which the current is changing. So we're going to have something where the current in the circuit is related to the rate of change of current in the circuit. Right? Okay, so we're basically going to try to do this quantitatively now, or finish doing this quantitatively. We've got our loop equation. And so now let's see, so this is a differential equation. I'm going to show you a little bit more how to solve it, but you don't have to know how to solve it. Okay, so let's simplify this, or just change this a little. I'm going to divide by R. So this is going to give me V over R minus I minus L over R di dt equals 0. All right, so remember, our goal is to find I of t. So you are looking for some function I of t such that when you plug it in here and you take its derivative and put it in here, then these will all sum to be 0. So it's going to have some V's and L's and who knows what else in here. But you need a function that will work for this, right? So this is a differential equation and that we're trying to solve. So again, you don't have to know how to do this, but I want to at least show you that this one is not that complicated to do, but you don't have to know how to do it. I know most of you haven't taken differential equations. So I'm going to define a function x of t just to help us along in doing this, to make this equation look like something more familiar. So I'm going to define a function x of t to be v over r minus I. And that's I of t. Okay, it doesn't matter. So if you knew what x of t was, you would know what I of t was. You'd have the answer because I of t would just be v over r minus x of t. So if you could find x of t, you'd be in good shape. And I want you to notice then, note that dx dt is minus di dt. Okay, fair enough, right? The time derivative of that, if I take the time derivative of both sides, I get dx dt here. This is 0 because v and r are constant. And so I'll get minus di dt. Okay, not clear how this helps us yet, but this is just some trick we're introducing because it will make this easier to do. So with noting this, we can see that we then have, so x, so there's x. So I'm going to just plug in for v over r minus I. That's x of t. So what I have is x of t plus L over r dx dt equals 0. And right, so I had a plus there because basically I just substituted di dt, or sorry, minus di dt for dx dt. So now you can see the reason we made up this function x of t and plugged it in here rather than just solving this differential equation. Because by just making this substitution, basically it's a change of variables. Now this looks like something we ought to be able to solve, right? So if I know the function x of t plus L over r dx dt is equal to 0, so then I can just do just move this to the other side. We're just going slowly here. Dx dt is equal to minus x of t, and that's really a function of time, times r over L. Okay? So I am looking now for this again, if I can just find x of t, I'm golden, because as soon as I have x of t, I can immediately get I of t by just doing v over r minus x of t. And this is not a hard differential equation to solve. We're looking for a function that's a function x of t such that its derivative is itself times r over L. Well, you know what functions are derivatives of themselves? It's exponentials, right? So if I solve this, so x of t is going to be equal to e to the minus, or any constant, e to the minus rt over L, right? Because if I take the derivative of this, I'll get minus r over L. If I take derivative of x with respect to t, I'll get minus r over L times this, which is x. So I'll get minus r over L times the original function when I take its derivative. Okay, and then just now all I have to do is put this back in for x of t, and that's easy to solve that for I of t. So once I have x of t, this tells me that I of t is equal to v over r minus this thing. And so that's going to be v over r times 1 minus e to the minus t. And I'm skipping a couple little steps in here. You can just do the arithmetic on your own. If you do this, you should get this with tau defined as L over R. Okay. All right. And one thing, if you didn't follow all of this, that's fine. If you did, good. And because people are in different places where in calc and differential equations. So if you followed it, wonderful. If you didn't, that's okay. But whether or not you followed it, you should, just as a sanity check, you should take this I of t, plug it back into here and make sure it works. It's not very hard to do. You just take its derivative and plug it in here, multiply by L over R, pick the function up here, and then you'll just cancel out a bunch of terms and you'll wind up with this sum actually being 0 for this I of t. So again, it's like you may not be able to integrate a particular function, but if somebody hands you the integral, you can at least differentiate it and check that it works. So that's the equivalent here. So here's I of t. You should make sure you can see how it works, or that it does work. Okay, so let's graph what this thing looks like as a function of time. Right? So this is t, this is I of t. So let's plug in, so at t equals 0, We'll have e to the 0, so that's a 1. So we got 1 minus 1, so that's nothing. So the current at time equals 0 is 0. After a long time, so let t get extremely large, then you get e to the minus large number, so you have 0 here, and so you got 1 in the parentheses, and so it'll go to v over r. So the current is going to approach v over r, which is kind of what you expected, right? At time equals 0, when you first close the switch, there's no current, and the current is going to ramp up from 0 to v over r after a long time. Because basically after a long time, the current stops trying to change. And as the current changes less and less, this thing has less and less backwards EMF. So it acts like a battery that initially has the same voltage as this. The current is 0. But over time, this gradually winds down to be a battery of voltage nothing. And so you just get V over R. And that's what we see in the graph of this function. After a long time, you get V over R. And in between, you essentially have an exponential fall toward this asymptote. Right? And as before, this this tau, which is known as the time constant for the circuit, just like we had a time constant for RC circuits, this thing tells you the typical time scale over which this thing rises to full current, right? So if we go out an amount 1 tau, so if we go out to a time equal to tau, then we're going to get 1 minus e to the minus 1. So 1 minus 1 over e. E is 2.7. So, I mean, it's just say about a third. So this is somewhere around a third. So everything in parentheses is around 2/3. And so it is the time at which the current has ramped up to V over R times 1 minus e to the minus 1, or 1 over e, which is about 2/3. Right? That thing's around 2/3. And then if you go out another time constant, you'll have the current is V over R times 1 minus e to the minus 2. So you'll fill in 2/3 of what's missing each time you go out another time constant of tau. Okay. Okay. And these exponentials appear, right? They don't just obviously appear in circuits and nuclear decay. And I know I did that example ages ago with bubbles. Any function whose rate of change is proportional to the amount is an exponential function, either rising or falling, depending on whether having the function grow adds to or reduces the rate. So wait, before I go on with that, question so far on this?
Could you re-explain the arrow with the note after that arrow? dx over dt is equal to negative di over dt. Yeah, this part.
Oh, yeah. Yeah, so if we define a function x to be b over r minus I, and now take the derivative of both sides of this equation. So here we get dx dt. Remember, x is this function of time. So take the derivative of this side, you get dx dt. Take the derivative of this, you'll get 0 minus di dt.
Oh, I got it. Maybe the voltage is not dependent on time.
Exactly right. Yep, voltage is this is just a fixed battery here.
Yeah, thank you.
Yeah, so V and R are both constants. Good. Yeah. What else? So, right, and anything that, again, the reason this exponentials appear so much, and generally observe that, exponential functions after sine, if you had to pick the most important functions, right, it's sines, cosine, and then next would probably be exponentials. They appear in huge ranges of physical problems. anything where the rate of change is proportional to the amount. And so, right, here's a simple thing. Just if you had, right, you don't need to cook up a complicated system. If I had a bucket of water and it were draining and there were a hole in the bucket, if the water itself, if every time a little bit of water flowed through the bucket, it wore away a little bit of the hole to widen it, I guarantee this would be an exponentially rising flow over time, right? It would start at some, depending on the size of the hole, it would start initially at some flow and would gradually rise. Because the rate of change, so this is the critical point in understanding exponentials, the rate of change of the water in the bucket, or the flow rate, is proportional to how much water has already flowed. Because the more water that flows, the larger the hole is. And the larger the hole is, the faster the water flows. So you can imagine, right? As the water flows, it widens the opening, and that which makes it flow faster. And the faster it flows, that makes it the opening even wider. And so you get this exponential runaway, right? You could also imagine a case where if you had a bucket of water, but the water were like depositing something here, so that it was shrinking the size of the opening as a function of time, then the flow rate of the water as a function of time would be an exponential decay. Because every time a little bit more water flows, the hole shrinks. And so you'd have a decay towards zero flow, or a rise toward infinitely fast flow. And of course, now we have all learned, we are doing this over Zoom because of the exponential function, right? The rate of change of the number of people with COVID is proportional to the number who have it. Assuming everybody, early on in the pandemic, when nobody knew what the hell to do and we were all washing groceries instead of wearing masks, right? So we were wearing masks, but whatever. If early on in a pandemic, right? In any contagious disease, the rate of change of the number of people who have it is proportional to the number of people who have it, right? So if there are 100 people who have it, it's growing twice as fast as if 50 people have it. And this exponential factor, if you look for COVID, right, this factor is what's known as A naught, except, well, there it's an exponential rise, but this factor, you'll get something like the number of people infected as a function of time is some initial number times e to the, let's just call this n0, A naught times t. This factor determines how bad a pandemic is, the contagiousness factor of the disease. It's essentially the time constant. How long do you have to wait if every day, sorry, I should have said that in a different way. Every day, if a single person infects 5 people, this factor is 5. If every day a single person infects less than 1 person, then this thing will gradually wind to 0. But if this is larger than 1, then you're gonna get an exponential runaway. Right? And so the idea of vaccination and herd immunity is you drive this number down, because the number of people who will be infected by every infected person it shrinks. And when this gets below 1, then you'll have an exponential decay towards 0. Okay, and then maybe at that point we can all come out of our bunkers. All right, so questions so far, and then we're going to do an actual example where we use this function. Okay, so let's look at a circuit. Although, sorry, one thing before we do that. So there's a way of thinking about, just think qualitatively about what would happen in this circuit. Let's suppose I have a voltage and I have a switch, and I need some resistor here. Doesn't really matter how much. And I'm going to have an inductance L. It's going to go around like this. And I'm going to have another loop in the circuit here. And I'm going to have a light bulb here.
Masterpiece, deserving of the Louvre.
Yes, thank you. All right. Yeah. Okay, good. So we have a voltage, a resistor, an inductor, and a light bulb. All right, so the question is, how bright is the bulb as a function of time? Right, so just stop and think about it for a second. Think about so do this on your own. You're not calculating anything. I just want to know, is it instantly off and gradually gets brighter? Is it bright? Does it get dimmer? Does it just stay constant in the middle, or what does it do? So to do that, I want you to think about the fact that the voltage across here, right? This is all one voltage and this is all a different voltage. So the voltage across the inductor has to match the voltage across the light bulb. All right, so just take a second and think about what that will do as a function of time. Okay, so what'll happen over time is initially when you first close this switch, the voltage across this opposes current going through it. So there's a large voltage drop across this, and we're going to do this example quantitatively in a minute, or an example like it in a second. But right when I first close the switch, there's no current, right? You know that current as a function of time looks like this. So when the switch is first closed, there's no current in the circuit, which means the voltage drop across here is nothing, because the voltage drop across a resistor is the current through it times the resistance. So there's no voltage across here. So if you're doing your loop diagram, you say plus V minus nothing. So we must have V volts across here. So which means the bulb is initially bright. Right? So the bulb is bright initially. And then over time, the current in this thing, the current rises. So there's more and more current through here. But if you look at it, the voltage across this, the voltage across an inductor is equal to its inductance times the time rate of change of the current through it. So initially, the time rate of change of the current is quite high, which is why the voltage across the inductor is high. But after a long time, the rate of change of current through it is almost zero, right? This gets very flat. And so the current is nearly constant, which means the voltage across here is basically nothing, which means all the voltage, so the voltage from there to there is nothing. That means there's no voltage drop across the light bulb, and all the voltage drop is across the resistor. So bulb gets dimmer over time. Okay, and I think probably we should, rather than doing this example quantitatively, is just going to take some time, and so there's no point getting 4 minutes into it and then stopping. So let's stop here, and then be sure to just plow ahead in the homework early. And I assume everybody got the notice about the change in the quizzes. So there's no quizzes the very last week, and I adjusted the syllabus so the quiz happens the week before the last week. The quiz on this stuff. Or I'm sorry, not on this. Sorry, the quiz on Faraday's law is this week, not next week. What am I talking? What is today? I've been in quarantine too long.
Today's Thursday.
Thursday, and I'm losing track of weeks, not just days now. Right. So next week is the last full week, and next week is when there is a quiz on Faraday's law. There is no quiz on this stuff because we'll be finishing it at the end of the semester. So here we are finishing this week. Next week, there is the quiz on Faraday's law. And then the last week, which is short, there are no quizzes, which is just, so I moved the quizzes back to be next week rather than the shortened final week. All right. Yeah, Jade, I'm sorry. That's, yeah, it's just quarantine has taken over my brain. Sometimes I can't remember. I look outside and I can't remember if it's spring or fall. So, all right. Yes, everything will be on the final. Yeah, fair inductance will be on the final exam, but no quiz on it because we won't finish it in time to give you a chance for the quiz. So yeah, it'll be on the final though. All right. See you all in office hours. Office hours have to be short today. So if you have questions, come early. Bye all.